Distributed Systems from Scratch. This is episode 7, Consensus Raft. Last episode, we tackled Paxos, the foundational consensus algorithm. It was correct, but it was hard. Hard to understand, hard to implement, hard to extend. Today, we learned the algorithm that most modern systems actually use. Raft solves the exact same problem, but it was designed from the ground up to be understandable. In 2014, Diego Ongaro and John Osterhout at Stanford published a paper with an unusual goal. Most papers try to be novel. This paper tried to be understandable. Their opening claim: Raft is designed so that it is easier to understand than Paxos and to provide a better foundation for building practical systems. They backed this up with a study. They taught both Paxos and Raft to graduate students, then tested their understanding. Raft won significantly. Let's see why. The core problem with Paxos isn't the algorithm itself, it's the gap between the theory and what you need to build. Paxos is specified as a single degree algorithm. It agrees on one value, but real systems need to agree on a sequence of values, a replicated log. The multi-Paxos extension that handles this was never formally specified by Lamport. The result: every team that implements Paxos ends up inventing their own variant. Google's Chubby team spent years debugging theirs. These variants are rarely published, so each new team starts from scratch. Raft was designed to fix this. It's a complete formal specification that covers everything you need: leader election, log replication, safety, and even membership changes. Raft's key insight is decomposition. Instead of solving everything at once like Paxos does, Raft separates consensus into three independent subproblems. This is a software engineering insight as much as a distributed systems one. When you decompose a hard problem into simpler pieces, each piece becomes easier to understand, implement, and verify. The three subproblems. First, leader election. Exactly one leader at a time. If the leader fails, elect a new one quickly. Second, log replication. The leader accepts commands from clients and replicates them to all followers. An entry is committed when a majority of nodes have it. Third, safety. Once a log entry is committed, it can never be lost, even across leader changes. This is the guarantee that makes the system correct. Each subproblem has a clean solution. Let's walk through them. Every node in a Raft cluster is in one of three states at any given moment. Follower, the default state, passive. Followers just respond to requests from the leader and candidates. They don't initiate anything. Candidate, a follower that hasn't heard from a leader, transitions to candidate. It starts an election by requesting votes. Leader, the candidate that wins the election. The leader handles all client requests, replicates log entries, and sends heartbeats to maintain authority. The life cycle flows naturally. Every node starts as a follower, becomes a candidate if it stops hearing from the leader, and becomes the leader if it wins an election. Raft divides time into terms. Each term is a period with at most one leader. A term begins with an election. If the election succeeds, the winner leads for the rest of that term. If the election fails, say due to a split vote, the term ends with no leader and a new term begins immediately with a new election. Terms act as logical clocks. Every RPC includes the sender's term number. If a node receives a message with a higher term, it immediately knows it's behind. It updates its term and steps down to follower. This is Raft's mechanism for detecting stale leaders. If a leader is partitioned and a new leader is elected with a higher term, the old leader will discover the higher term as soon as the partition heals and step down immediately. Subproblem 1: Leader election. This is arguably the most elegant part of Raft. Here's how it works, step by step. Every follower runs a timer, the election timeout. This timeout is set to a random value, typically between 150 and 300 milliseconds. Random This is important. The leader sends periodic heartbeats, empty append entries messages, to all followers. Each heartbeat resets the follower's election timer. If a follower's timer expires without receiving a heartbeat, it concludes the leader is dead. It transitions to candidate, increments its term number, votes for itself, and sends request vote RPCs to all other nodes. Each node votes for at most one candidate per term. First come, first served. If a candidate receives votes from a majority of nodes, it becomes the new leader. The new leader immediately sends heartbeats to all nodes to establish its authority and prevent further elections. Remember the dueling proposers problem from Paxos? Two nodes start elections at the same time, split the vote, and neither wins. They retry, split again. Live log. Raft solution is beautifully simple. Randomized election timeouts. Each node picks a different random timeout. One node will almost always time out first. It starts its election and wins before the other nodes even realize the leader is gone. In the rare case of a split vote, each candidate picks a new random timeout and tries again. The probability of repeated split votes drops exponentially. Simple, elegant, and it works with extremely high reliability in practice. Let's walk through this visually. We have four nodes. N1 is the current leader. It sends heartbeats to N2, N3, and N4. Then N1 crashes. The heartbeats stop. N3 has the shortest random timeout, say 180 milliseconds. Its timer fires first. N3 becomes a candidate, increments to term 2, votes for itself, and sends request vote to N2 and N4. N2 and N4 haven't started their own elections yet. Their timeouts are longer. They see N3's request, verify that N3's term is current and its log is up to date, and grant their votes. N3 now has 3 votes out of 4, a majority. N3 becomes the new leader and immediately starts sending heartbeats. The entire process, from leader crash to new leader established, takes a few hundred milliseconds. Subproblem 2, log replication. Once we have a leader, how does it replicate data to all followers? The process is straightforward. A client sends a command to the leader, like set x to 5. The leader appends this command to its local log. It doesn't apply it to the state machine yet. That comes later. The leader sends append entries RPCs to all followers, containing the new log entry plus some metadata for consistency checking. Each follower appends the entry to its own log and replies with success. Once the leader has received successful responses from a majority of followers, the entry is committed. The leader applies it to its state machine and responds to the client. Followers learn about the commit through the leader's next heartbeat, which includes the updated commit index. They then apply committed entries to their own state machines. Here's what the log looks like across nodes. The leader has 4 entries. X gets 1, Y gets 9, X gets 2, and Z gets 3. The first 3 are committed. They've been replicated to a majority. The fourth, Z gets 3, is not yet committed. Follower 1 has all 4 entries. It's fully caught up. Follower 2 only has the first 2 entries. It's behind. Maybe it was briefly disconnected. The commit index is at entry 3. X gets 2. That entry exists on the leader and follower 1, 2 out of 3 nodes, a majority, so it's committed. Follower 2 is behind, but that's fine. The leader will keep sending append entries to bring it up to date. The committed entries are safe regardless. The commitment rule is simple but powerful. An entry is committed when it's been replicated to a majority of nodes. Once committed, it will survive any future leader election. Why? Because any new leader needs votes from a majority, and any majority overlaps with the majority that committed the entry. At least one voter has that entry, and Raft's election restriction ensures that voter won't vote for a candidate whose log doesn't include it. The leader never overwrites its own log. Only followers overwrite their logs, and only to match the leader. Data flows one direction. Leader to followers. Subproblem 3, safety. This is what makes the whole system correct. Raft enforces a critical safety rule during leader election. A voter will reject a request vote if the candidate's log is less up to date than the voter's own log. How do you compare logs? Two rules. If the last entry in one log has a higher term than the other, it's more up to date. If they have the same last term, the longer log is more up to date. This is called the election restriction, and it's the key to Raft's safety guarantee. It ensures that a node with a stale log, one that's missing committed entries, can never win an election. Only nodes with the most complete information can become leader. This means every new leader's log contains all previously committed entries. No committed data is ever lost, even across multiple leader changes. Let me connect this back to the quorum argument. A committed entry exists on a majority of nodes. A new leader needs votes from a majority of nodes. These two majorities overlap. At least one voter has the committed entry. That voter will reject any candidate whose log doesn't include that entry. So the winning candidate, the new leader, necessarily has all committed entries in its log. This is the same quorum overlap argument we saw in Paxos, but in Raft it's cleaner. There's no need to track proposal numbers or previously accepted values. The log comparison does all the work. Here's something remarkable. The entire Raft protocol uses just two RPCs: request vote, sent by candidates during elections, contains the candidate's term and log information so voters can check the election restriction. Append entries sent by the leader for both log replication and heartbeats. An empty append entries is a heartbeat. A non-empty one carries new log entries. Two RPCs, that's it. Compare this to the multiple message types in Paxos: prepare, promise, accept, accepted, plus whatever your multi-Paxos variant adds. Raft's simplicity is a feature. Let me put Raft and Paxos side by side. Approach. Paxos is symmetric. Any node can be a proposer. Raft uses a strong leader. One node drives everything. Specification. Paxos specifies single decree only. Multi-Paxos is informal. Raft is a complete specification covering everything: election, log replication, safety, and membership changes. Leader election, not specified in Paxos. In Raft, it's a clean state machine with randomized timeouts. Log gaps possible in Paxos, requiring a fill-in protocol. Impossible in Raft. The leader fills gaps before committing. Understandability. This is the big one. Raft was literally designed and tested for understandability. The user study in the paper confirms it. Safety, identical guarantees. Both algorithms provide the same correctness properties. Raft is not weaker than Paxos. It's equivalent. Raft is everywhere. etctd, the backbone of Kubernetes. Every piece of cluster state, pod definitions, service endpoints, configuration is stored through Raft consensus. If you're running Kubernetes, you're running Raft. CockroachDB uses Raft per range. Each range is a shard of data, and each shard is its own Raft group. A large cluster might have thousands of simultaneous Raft groups. HashiCorp console, service discovery, and configuration uses Raft for its consistent key value store. TiKV, the distributed key value store under TiDB, uses multi-Raft with thousands of groups for horizontal scaling. Even RabbitMQ's quorum queues use Raft for replicated durable message ordering. Raft isn't perfect. The strong leader design has real trade-offs. All writes go through the leader. If your client is in Singapore and the leader is in Virginia, every write pays cross-continent latency. There's no way around this with Raft. The leader is also a throughput bottleneck. One node handles all writes. You can scale reads, followers can serve stale reads, but write throughput is bounded by the leader's capacity. And Raft doesn't handle Byzantine faults. It assumes all nodes are honest. A malicious node can break safety. For Byzantine fault tolerance, you need PBFT or similar protocols. which we'll cover in a later episode. These aren't bugs, they're trade offs. Raft trades flexibility for understandability, and for most systems, that's the right trade. If you read one paper from this entire series, read the Raft paper. It's called In Search of an Understandable Consensus Algorithm. It's 18 pages. The writing is clear. The diagrams are excellent. The specification is complete enough to implement from. And if you want to see Raft in action, visit raft.github.io. There's an interactive visualization where you can trigger elections, crash notes, and watch the protocol respond in real time. Let's recap. 1. Raft decomposes consensus into three clean sub-problems: leader election, log replication, and safety. 2. Randomized election timeouts prevent split votes, elegantly solving Paxos' live log problem. 3. Committed means replicated to a majority. Once committed, an entry is never lost, even across leader changes. 4. The election restriction ensures new leaders always have all committed entries in their logs. The quorum overlap argument guarantees this. 5. The entire protocol is just two RPCs: request, vote, and append entries. Complete, simple, buildable. Next episode: replication. We've been using the word replication throughout the consensus episodes, but replication is a bigger topic than consensus alone. There are multiple replication strategies: single leader, multi leader, and leaderless. Each has different trade offs for consistency, availability, and performance. We'll explore all three, see how they connect to the consistency models from episode 5, and understand why systems like Dynamo chose a fundamentally different approach from Raft. That's episode 7, Raft Consensus Made Understandable, the algorithm behind etcd, CockroachDB, and thousands of production systems. Next time, replication. Thanks for watching.